This was a really informative session. So we will move on with the next session. Let
Okay,
Mr.
so
Dr. Kaushik, sir, a few
yeah,
minutes. I will just quickly introduce you and we can start.
okay.
So Dr. Kaushik Das received the BTech degree in Metallurgical Engineering from Bengal Engineering and Science University, Shibpur, India in 2005, and he holds a ME degree in Material Engineering from Indian Institute of Science, Bangalore in 2007, and a PhD degree in mechanical engineering from McGill University, Montreal, Canada. He works as a he worked as a process development engineer in C2MI, Bromont, Canada, from 2012 to 2014. Thereafter, he joined Indian Institute of Technology, Bhubaneswar, as an assistant professor in the School of Minerals, Metallurgical and Material Engineering. In 2019, Dr. Das joined the Department of Metallurgy and Materials Engineering of Indian Institute of Engineering, Science and Technology, Sipur, and is presently working there as an associate professor. His research is focused on computational and experimental approaches to study quasi-static and dynamic mechanical properties of advanced material in form of superalloy.
Okay, am I audible?
Yes, sir. You're audible.
Okay, so let me try to uh, share my screen. Okay, so share a window or a screen, entire screen. Let me share my entire screen. Okay, I will. Uh, okay, is my screen visible to you? Mm, hello,
Yes, sir, it is visible.
is the PPT visible?
Yes, sir. Your PPT is visible.
Okay, so let me go to full screen mode and let me start. Okay, so this is the fourth session, and in this session of this one-day workshop, and in this session I'm going to demonstrate how OF2 is integrated with Mutumic. Right. So basically, I will be focusing on the part where the previous speaker, uh, Albert, where he had left off. Okay. Okay, so this is where Albert had left off, right? So he had shown that once you create the microstructure, right, and you give some kind of like inputs on the OF2 uh, this window, you can then get the results, right? Which results we are talking about here? Only that what we have done up to this point, we are only going to look at the elastic properties. Elastic properties meaning the Young's modulus and the Poisson's ratio, but there is a lot more that one can do. Okay, now for this, as you had seen, you need to install OF2 on either the local computer. It's possible that once you have the image that is generated by Mu2Make, right, you can save that image. It can be in a PNG format, TIFF or JPEG format, and you can either do this analysis on the Param systems, or you can do it on your own workstation at your own institute. Okay, so um, okay, so OF2 is basically it's a short form for object-oriented finite element method, right? Two means it is only for two-dimensional images. There is another software called OOF 3D. So there you can handle 3D kind of like microstructures, right? Which Mu2Make can also generate. But that takes a lot of computational, let's say, resources, and that unfortunately you will not be able to run on your workstation. You can only run that using a high performance computing facility. Okay, but today the demonstration that I'm going to give you is only going to be based on the two-dimensional images that are generated by Mu2Make. Okay, okay, so at the heart of this OF2, it's a finite element package, right? So what is finite element method? So finite element method is a numerical tool that is used to solve partial differential equations. And as we all know, the description of laws of physics for the space and time dependent problems are usually expressed in the form of partial differential equations. Even though the problem we are dealing today, the problem of elastic deformation, does not have any time dependency, but still it is expressed as a partial differential equation, and they are solved using finite element method, right? So for vast majority of geometries and problems, the partial differential equations, they cannot be solved analytically, and you have to use numerical techniques to solve the partial differential equations. And finite element method is one of those many available numerical techniques, and it is one of the most popular, right? And so any problem, it's not only limited to mechanical behavior of materials, whether it is electrical, dielectric, or any other like thermal. If your problem can be defined by a partial differential equation, it can be uh, theoretically be solved using the uh, finite element method, right? What does the finite element method do? It is based on discretizing the problem into finite domains. For example, look at the plot below where you have u as a function of x. The blue curve is uh, the analytical solution, right? But this analytical solution is very difficult to get. But what you can do is, if you look in the inside, there is a red dashed line, right? So you break up this domain x into this is a continuum. So you break it up into continuum is infinite, right? So you break it up this infinite domain into finite number of segments, right? So you have broken it up in only 9 segments here. It is not needed that the segments will all be in equal in dimension or equal in length. They can also be unequal. And once you do that, then you are able to find the numerical solution, which will be very close to, which is shown by the dashed red line, which is very close to the actual solution, right? So u is the this u is the actual solution of the partial differential equation, and uh is the numerical solution, right? And uh, how do you get it? You get it in terms of some coefficients ui and multiplied by psi I, right? Psi I, what are the psi I? Psi I are called the basis functions that are used in finite element method. So with this small introduction, let's get into the uh, application of the finite element method for our problem, right? For our case. Okay, so if you can do that for a curve, right? If you can discretize a curve like that, definitely if you have a three-dimensional or a two-dimensional geometry, as is shown in the cantilevered structure on the left, you can discretize that 3D volume or a 2D volume or 2D area into finite elements as shown here, right? And what are the type of elements you can do? There are different types of elements available. For 2D, it can be triangular, rectangular, or quadrilateral or rectangular type. But in 3D, there can be other 3D shapes like prismatic, tetrahedral, pyramidal, and hexahedral. These kind of elements are available in many open source as well as commercial software. Okay, so what are the basic steps of microstructure based finite element methods? The first step is to convert the microstructure to a geometry that the finite element software can handle, right? So that is the first task. Okay, we will see where the difficulty lies in a slide or two. Why cannot all finite element softwares handle a microstructure, a 2D image, right? It's difficult for them. That's where the OOF2 comes in with its advantage. In step 2, we will have to define the appropriate material models inside OOF2. In step 3, we assign the material properties to the identified domains. Right, which material properties we will see. In step 4, we will have to mesh the finite element model. Basically, we'll have to tell how many elements on the x and the y direction. And in step 5, we will have to assign appropriate boundary conditions to solve the model, right? Basically it's a partial differential equation, right? Partial differential equations, as you all know, they need to have initial conditions, boundary conditions. So in finite element method, we call all those conditions as the boundary conditions. So those have to be specified. Otherwise, your problem cannot be solved, right? It is unsolved. Without boundary conditions, partial differential equations are unsolvable. In step 6, we have to calculate the volume or the area averaged certain parameters called stresses and strains, right? We'll have to, because we are interested in mechanical properties, we will have to calculate these. Okay. And in step 7, finally, is the post-processing step. We evaluate the effective properties from the averaged stress and strain values that we have calculated. Okay, so first let's start with step 1 with the processing of the microstructure. Now, whenever we look at a microstructure, right, if you see any kind of microstructure, there are, if it is a multi-phase microstructure, we identify the phases by their colors, right? So they are of different colors, and in terms of images, we say that they have different properties or different pixel values, right? So either they can be grayscale values or they can be red, green, blue values, right? And for example, in the image that you show below, the dark gray regions belong to phase 1 phase, the light blue, the light gray regions in between, they belong to the second phase, right? So we can identify them to be different phases, and we can club them under different pixel groups. For example, the regions with the dark gray phases, we can club them under pixel group 1, and the regions with the with this light gray phase, we can club them under pixel group 2. Okay, so once we have discretized, we identify the different pixel groups. Next, what we have to do is step 2 is use appropriate material model. In our case, we'll be doing a linear elastic analysis, and so the law that we shall be using is the simple Hooke's law, right? Which states that stress is sigma is related to strain epsilon by the stiffness tensor C ijkl, right? So the stress and strain, they are second rank tensors, and they are related to one another by this fourth rank stiffness tensor, right? So it is very difficult to deal with things that are of rank 4. So we convert that by some mechanism to this uh, the 6 cross 6 matrix, right? So for a given anisotropic material, the stresses and the strains can be written in the matrix form in this fashion, where you have the 6 independent stress components on the left hand side, 6 independent true strain components, right, like epsilon 1 1 2 2 3 3, and this twice epsilon 2 3, this is twice because you are talking about the shear strains, right? So they are on the right hand side, and in between in red are the stiffness components. And for a completely anisotropic material, you would need 21 independent stiffness components. For an isotropic material, life becomes much simpler. You can use only 2 independent stiffness components, C11 and C12. For the cubic material that we will be talking about today, we will need 3 independent stiffness constants, C11, C12, and C144. And if you remember, these are the ones that were discussed, that was shown by Albert on his last slide. Okay, so now let's look at the problem that most finite element software have. The problem is that we have to build a conforming mesh. What do I mean by conforming mesh? So let's say you have the image on the left, right? So this is an image, and I have divided it into square meshes, right? So, but the problem is that the boundary of the square meshes, they do not match with the boundary of these different colored regions, right? We have to do that. To doing so is conforming. So we do that by creating a skeleton, and once we do that, that is where OOF2 is very powerful in OOF2 has a great advantage over other softwares. You end up with a mesh that looks like the figure on the right, and in this figure you see the boundaries of the elements, they match with the boundaries of the different colored regions. Okay, so we have the mesh boundary, element boundaries, and the phase boundaries, they match, they conform. So this is what is known as a conforming mesh. Okay, another thing before we go on in our discussion is to understand the how we select the we, or in this case OOF2, selects the skeleton. They do so by a process of minimization of an energy term. It is not energy per se, but the authors of the code, they call it energy, right? That parameter energy, and this parameter energy is a function of homogeneity and shape of the element, right? So this energy is equal to alpha homogeneous plus 1 minus alpha E shape, right? The shape energy. What do I mean by this E homogeneous and E shape, let's look at the image on the left. If your element is entirely within a single color or within a single phase, then it is called a homogeneous element. If the element is shared by multiple colored regions or multiple phases, then it is heterogeneous, or in this case the value would tend to 1, and in the previous case the value would be 0. And if the shape is regular, for example an equilateral triangle or a square, the shape energy would be 0. If the shape is completely irregular, for example this squished or this irregular triangle or this rectangle, right, with a very high aspect ratio, the shape function, the shape energy would tend to 1, right. So the goal of the skeleton selection is to minimize this energy based on this homogeneous nature and based on the shape of the element. Then we have to apply boundary conditions, and when we are going to apply boundary conditions, uh, there are two types of boundary conditions that are applicable in the finite element method, especially in the domain of mechanics. One is called the Dirichlet boundary condition, which is the simplest to code. And what we do is that in Dirichlet boundary condition, let's say we have a rectangular structure like that, we apply displacements on the outside edges, right? On this edge, on the right edge. Um, in this particular case, we have applied a strain of a normal strain of epsilon 1 1. Okay. So on faces or side where displacements are not prescribed, the component of the displacement normal to that face is considered to be constant. There's another type of boundary condition called the periodic boundary condition, which requires a periodic mesh, right? It also requires a periodic microstructure. We are not going to look at periodic applying periodic boundary conditions today. We are only going to limit ourselves to Dirichlet boundary conditions, okay, which are the very simplest to code and very easy to demonstrate. Okay. Now, what are the partial differential? What is the partial differential equation we will be solving? We will be solving the simple force balance equation. So this is the tensorial form of that equation, right? So the sigma ij comma j plus Fi is the body force, right? Sigma ij is the stress. So this is the stress gradient plus body force is equal to 0. Usually in our problems, the body force term goes to 0, right? So we can neglect that. Once we have solved this equation, what the finite element software gives, it gives us the as solution the value of the nodal displacements and the value of the stresses at each node. Okay, and from there, once we have that, we can calculate the area average stress as summation of the stress multiplied by the area of each element, and we do the summation for all elements divided by the total area. That would give us the area average stress. Similarly, we can get the area average strain as well. So strain is the product of the strain component multiplied by the area of each element, and then we do the summation of this product for all the elements in that area. Then we divide it by the total area. So that gives us the area average strain. Once we get the area average stresses and strains, then we can calculate the elastic properties, at least for this linear elastic model that we are considering, using the formula that we are given below. So the elastic modulus along the x direction is the average stress sigma xx divided by average strain epsilon xx, right? And the Poisson's ratio mu xy is the negative of the strain along normal strain along the y direction divided by the normal strain along the x direction. So these are the equations that we will need for the evaluation of the elastic properties. Okay. Okay, so let's look at, this is the example problem that we shall be looking at. So let me first describe the problem for you, then I shall go into the actual software. So we have to identify, so this is the microstructure that I will be looking at. This is a microstructure of a nickel aluminum superalloy, where the violet or the blue region is the gamma phase, and the orange region that you have, or the yellowish region that you have here, is the gamma prime phase, right? So both have cubic, both have cubic crystal structures, right? Both are cubic, and so each phase is associated with a color of different pixels, right? And once we do that, we can form different pixel groups for the different phases. Okay. Then what our goal would be? Our goal would be to create a model, as I have shown here in this step. What I want to do is I want to keep the left edge fixed such that it cannot move along the x direction. Y direction it can shrink, right? Similarly, for the bottom edge, I want to make sure that it cannot move along the y direction, but it is free to move along the x direction. On the right edge that you have here, I will apply a specific displacement, and that displacement would be equal to some strain value multiplied by this length, right? L is the length of the this square microstructure. Top edge, we will specify nothing. We will make it with the software will calculate and we will deform accordingly. Okay, so how do we assign material properties to each phase or pixel group? As we shall see, we will define the elastic stiffness matrix in the OOF2 software in this way. So this is a 6x6 stiffness matrix, and since this is a symmetric matrix, only the top half is provided. And as you see, the values can be put in, and we will just demonstrate to you how we can do that. Okay, so once we have the properties, we have to create a finite element mesh, which is shown here. So this is how the finite element mesh would look like. And then we will assign appropriate boundary conditions. In this case, we are doing a tension test along the x-axis, right? So once everything has been set, we will set an appropriate finite element solver. I will show you how we shall use the very default values that are there in the software, and that will give us results for today. And once we have the results, then we can do what is known as post-processing, and that will give us the different kinds of stress and strain and stress distribution in the microstructure, right? So this also we can generate. If time permits, we shall also do that today. Okay, so these are some of the results that we have of the work that we have done with OOF2 and Mu2Make, right? So we have generated microstructures at different temperatures for this nickel aluminum superalloy with gamma gamma prime microstructure, and we have created the meshes, and we have looked at how the stress distribution is at different pixel sizes, and we have calculated the results based on the microstructure for at different temperatures, right? So we have done that, and we can also look at the effect of annealing, right? What is the effect of annealing on the microstructure? That we can also study by analyzing the microstructure in OOF2, and the results are shown here. So these are some kind of studies that are possible. Another thing that we can also do is the elastoplastic analysis, but unfortunately, at this point of time, it cannot be done in OOF2. Right? Of course, there are some extra modules that the authors are trying to add as we speak. Right? The next version may have this added facility, but as of now, what we are doing is that we are exporting the model that or the mesh that we generate in the OOF2 to a commercial finite element software called Abacus, right? And within Abacus, we can do different kinds of elastoplastic analysis. So, for example, in Abacus, we can assign different regions, just like we can import the mesh from, or we can export the mesh from OOF2 to Abacus, and we say that, let's say the first phase, which is the continuous phase, we have the elastic properties, and we also need to know their plastic properties, right? So this is the stress strain curve for that. For the green region here, we also need to know the elastic properties as well as the plastic properties. So once we know both the elastic and the plastic properties of the individual phases of the microstructure, we can find out their effective elastoplastic response. So the procedure is almost similar. So we can do the same kind of tension test there, but now we can look at the plastic response, right? So we can find the average, determine the average equivalent plastic stress and average equivalent plastic strain. So these things are not possible within the OOF2. We have to export, take the mesh from OOF2 to a finite element software, and there we can do all these things. Okay, so effectively what we do in this cases is we generate the mesh in OOF2, we import the mesh to Abacus in the format of an Abacus input file, which ends with star.inp. So OOF2 allows us to do that. It allows us to save the file in a format, in this INP format. I will show you how. It allows us to apply the elastoplastic, then we apply the elastoplastic material properties for each phase, and we set up the analysis with time increments. We apply periodic boundary conditions, and we solve the problem. And once we get the output, we can visualize what the deformed shape would be, and we can get the effective stress strain response from the after post processing. Okay. Okay. So I think we are to summarize what we have shown, or what I will be showing you, is I will demonstrate you in the next half an hour. I will walk you through the OOF2 software to see how we can evaluate the effective properties. But as I want to impress upon you that the OOF2, the Mu2 make can also generate 3D microstructures, and these 3D microstructures can also be used to predict the effective. We can also predict the effective properties of the 3D microstructures, but for that we need a different software called OOF3D, which is also open source, available from the same NIST website, right? And once we generate the microstructures, we can export them to Abacus. What can be done in Abacus? All different kinds of things. We can do periodic boundary conditions to simulate realistic mechanical loading. We can look at the effect of coherency strain if it is a precipitation hardening alloy. We can also study the effective elastoplastic properties of multi-phase microstructures. And so basically, crystal plasticity studies can also be done once you export your mesh from this OOF2 or OOF3D to Abacus, right? So I think with this, I will uh, end the uh, presentation part, and what we shall what we shall do is we shall go into the demonstration, right? So for that, um, let's see. Okay, so um, okay, so I have this Ubuntu Windows subsystem for Linux on my laptop. So I will open OOF2 by just typing OOF2. If you have installed, or if you plan to install OOF2 on your individual systems, you can do it in this way. Otherwise, if you plan to do it on the Param system, there are certain commands that have been provided to you. Follow that route. So I type in OOF2, and if I type it, the OOF2 main software window is going to open up, right? And the message window is there. Let me take the message window and place it in a proper place, right? Okay. Next, what I want to do is I want to start by going to this microstructure, right? So I go onto the microstructure and I select my microstructure. I will click on new from image file, and if I click on new from image file, I will go to the folder where my image file is saved, right? I will go to, I will just navigate to my folder. Let's see. Mm, yeah, it's on desktop, and on desktop it is in, yeah, this C-2025, and I will use this. I'll select my file name 900k underscore t3.png. There's things, microstructure name, height, width. If you want to change, you can, but you can leave them automatic. That's the easiest way. Okay. So once you do that, you can see that this is a 1024 cross 1024 pixel microstructure or pixel image, and it is loaded, right? To have a better look, what I suggest is go to the Windows, go to graphics, go to new, right? And new, what I will move my graphics window to this side here, make it a little bit bigger, and I will go to layer, I'll go to new, and I will go to image. Okay, and I will click on OK. So this is the microstructure you would see on the graphics window. Another thing that you can do will make your life much easier is go to, at this stage, go to settings, go to new layer policy, and in the policy equal to never, make it policy equal to single, right? So that will update the graphics window every time we do a new task. Otherwise, we would have to do it manually. Okay, press OK. Okay, so now that our microstructure is loaded in OF2, next uh, uh, we have to assign different pixel groups. Okay, so how do we do that? We will go to this, we go to the toolbox and we click on the drop down arrow here, and from the choices we click on pixel selection, and the method we will change to burn, right? So what does this burn do? It basically selects pixels of the same color or the same pixel value using a forest fire algorithm. Okay, so next what you shall do is we shall go to um, pixel groups. We'll go to click on new, and we shall name the pixel group as gamma. Okay, and so we'll click on OK. So if you do so, you see the gamma has 0 pixels right now. So next we will click on anywhere in the continuous phase. Let's make this a little bit bigger. Okay, so we'll click on anywhere on this continuous phase. If we do so, you see all the pixels having the same blue color, they have been selected. So once we have done that, we'll go back to the microstructure main OF2 window and we'll click on add. So once we do that, you'll see the pixels assigned to the gamma pixel group is now 481151, right? So, and what about the rest? In order to do the rest, we'll go to come back to our graphics window and you click on the invert button that is right here. So what we invert it, the other uh, pixel group will be selected, right? So this works only if you have a 2 color image, right? Okay, so then we will go to the main microstructure window and name the name, click on new and name the pixel group as gamma prime, and we shall click on add. Okay, so once we click on add, we have a new pixel group with 567425 pixels, right? So we have all the pixel groups selected. Now what we can do is we can go to our graphics window and go back to the viewer mode. Okay, and if you want to get a bigger image, we can click on fill. Okay, so that makes the image bigger. Okay, so our microstructure has been selected. We have selected the different pixel groups. Next, we go to the material. We have to assign the material properties, right? So, we have to, yeah. So we go to materials, and as you see, there are different material properties that can be assigned in OF2. So it's not only the mechanical properties. If you want to do the thermal properties, electrical properties, or if you want to do different kinds of coupling, such as thermal expansion, piezoelectricity, piezoelectricity, those also can be done using this OF2 software, right? But today, for our example demonstration, we are doing only the mechanical elastic analysis, and we shall click on the elasticity under mechanical, and we shall click on anisotropic, and we will click on cubic. Why? Because both our gamma and gamma prime phases are cubic phases. We'll click on uh, we'll click on copy, and if we click on copy, we ask for a name, so we will call it gamma underscore elasticity. Okay, so that will create one parameter, right? We will copy that again, and we shall name another uh, property called gamma prime underscore elastics, and we click on OK. So gamma prime elasticity and gamma elasticity and gamma prime elasticity has been created, and since they are anisotropic properties, we'll also have to specify their orientation. So we will drag, we'll go scroll down, and we click on the orientation property. We'll copy it again, and we shall name it as gamma underscore orientation, and we will copy that once again, and we shall create another property called gamma prime underscore orientation. So we have 2 properties for orientation, 2 properties for cubic anisotropic elasticity. Okay, so once we have done that, let's look at what are the elastic properties. So these are the elastic properties at 900 Kelvin for the gamma and gamma prime phases that we shall use. So for doing that, we'll click on the gamma elasticity and we'll click on parameterize. Once we do that, the values we will put in here. This is 213. C11 for gamma is 213.111. This is in GPA. So I will put in Pascal, so capital E9. So that's what the value becomes in Pascal. C12 is 149.649 E9. So that's the value that there. And finally, C44 value is 99.825 E9. Okay. So we have inputted the value of the gamma elasticity. We'll click on OK. Gamma prime elasticity, similar way, we will click on parameterize, and here we will use the value 210.756 E9. Press enter. For C12, we will use the value 149.316 E9, right? Because the values are given in gigapascal, we want to use the values in Pascal, right? And C44 is 105.513 E9. Okay, enter. So all our values of gamma and gamma prime elasticity are given. Gamma orientation, we will double click on that, or you can click on parameterize, change that to XYZ convention, and everything is 0, right? And for the gamma prime orientation as well, we will make everything XYZ, everything is 0. We are assuming that the gamma and the gamma prime phases are oriented in the same direction, right? If they can be oriented in different directions, but for our problem here today, we are assuming the simplest case. Then under materials, we will click on new, and we shall create a material called gamma underscore mat. Okay. And with material type bulk, we'll click on OK. Okay. So now we shall go to gamma elasticities, click on there, and there's a button called add property to material at the at below, right? We shall click that, and then you will see mechanical elasticity and anisotropic cubic gamma elasticity is listed under gamma underscore mat uh, underscore mat. Similarly, we will click on gamma orientation, and we shall click on add property to material, and it will be listed there. Okay, so this has been listed for gamma mat. Next, we assign this material properties to the pixel. So we will click on assign to pixels, and this window will open up. In the pixels, we will select gamma. Okay, and we will click on OK. So these properties have been assigned to the gamma. Next, we will create a new material called gamma prime underscore mat. Right. We'll click on OK. And just like what we have done for gamma, we'll click on gamma prime underscore elasticity. Make sure that the material is gamma prime underscore mat, and click on add property to material. We'll scroll down, click on gamma prime underscore orientation, and again click on add property to material. Once these two properties are there, we will click on assign to pixels, and we shall assign it to gamma prime, and we will click on OK. So both our gamma and gamma prime are assigned. So if you look in the message window, you will see that every time we are doing something, it is creating a kind of a command, right? So it is creating a Python command that we can save later. Okay. So that being done, we can close this our elastic properties um, text file. Okay. And so material properties have been assigned. Next, we shall go to creating the skeleton, right? So we'll go to skeleton. Right now, there is no skeleton. Let's click on new, and we shall, let's see, we will have a skeleton with 25 skeletons along the x-axis, 25 along the y-axis. We will use a tri-skeleton. And since our microstructure is periodic, because whatever is ending on the left side, it's there on the beginning on the right-hand side, right? Whatever is there on the top, you will see the corresponding edge on the bottom as well. So this is a periodic microstructure. Make sure that these two, left right periodicity and top bottom periodicity boxes are unclicked. You do not touch these two boxes if your microstructure is periodic. If it is not periodic, only then you will select, and you shall select these two boxes. Okay, so then let me click on OK. So once you click on OK, so you see the a skeleton has been generated. So this is the activity viewer. Let's move the activity viewer to the bottom here. So right now the homogeneity index of this microstructure is 0.918667. You can look at the microstructure and see that it has been discretized into triangular elements, but the edges of the triangular elements do not match with the phase boundaries, right? That is something that we have to do. There are different options like simple auto that will allow you to do so, but they are very memory intensive. Auto is extremely memory intensive. Simple is sometimes is in most cases wrong, right? So let's do it in the proper way. So next what we will have to do is we will go to the skeleton selection, right? So we will scroll down and there is something called skeleton selection. We'll go there, and there we want to select the elements. The method we select by homogeneity, right? The threshold is 0.9, so only those elements which have homogeneity index lesser than 0.9 will be selected. We'll click on OK. So once we do so, you see they are highlighted here. 322 elements have been selected. So these are the elements which have homogeneity index lesser than zero 0.9. What do we do with that? We go to the skeleton window, and there we will use refine. Which elements do we want to refine? We want to refine the selected elements, right? And we will use bisection. Alpha value is 0.5. So a value of 0.5 for alpha gives equal weightage to the homogeneity as well as to the shape, right? Uh, so we do that and we click on OK. Once we click on OK, you see the selected elements, they have been bisected and you have further more elements, right? So, and also you note that the homogeneity index has also increased from 0.91 to 0.956, right? So you can do this process again and again to make your homogeneity index closer to 1. But for today's case, we will stop right here because we don't have time, right? So next what we shall do is we shall um, go to skeleton selection once again, right? We will select this method, select by homogeneity, and we shall again click on OK. If you click on OK, you see only now these are the elements which have homogeneity less than 0.9. Okay. Then what we do is we go back to skeleton. So there is going back and forth between skeleton and skeleton selection windows if we want to have a good, well-defined conforming mesh, right? So we go to we click on the method drop-down box and we shall go to snap nodes, right? Snap nodes, but not the all nodes. We only want to snap nodes. What does it do? It moves the nodes directly to the pixel boundaries. So this is one tool that OOF2 has, a very useful tool. So we will use that and we'll click on OK. So once we do that, you see, not much has changed, right? So there is no change, you see, because everything was quite good. So snap nodes has been done. Then we shall finally do rationalize. We will do it for all elements, right? And we'll click on OK. And what it does is it tries to search and try to remove bad triangles. Luckily, we don't have any. So rationalize has been done. We will finally do a final check. We will try to fix any kind of illegal elements that are there, right? So we will click on, we will method fix illegal elements. We'll click on OK. So again, no illegal elements were found and hence none were removed. Okay. So once we have gone to the skeleton, then we shall go to FE mesh, right? So this is the step where we can create the mesh. So this is empty now, mesh information, no mesh. We'll just click on new. We click on new, so this create a new mesh window comes up. We'll use all the default values and we'll click OK. Once we click OK, you see a mesh has been generated with 1422 nodes and 2672 elements, right? So once this has been generated, this gives us a, at this point you can save, right? So you can click on the save button here and it will allow you to save your mesh. So you can call this 900k underscore t3 underscore mesh, and you can name it as .inp, and you can change the format to abacus, right? So if you do that, it will save the mesh in a format that can be exported into abacus. This inp or the input file that you have just generated, you can export into abacus if you want. You click on OK and you will see that that file has been saved. Okay, it has been saved in the folder that you had specified. Okay, so the mesh has been generated. Now what we will do, we will go to this fields and equations. So this is our mechanical problem. So the displacement has to be defined. It is active, and the equation that we will be solving is a force balance equation, and the problem that we are solving is a plane stress problem, right? So in mechanics there are problems of plane stress and plane strain. For 2D structures like this, the problem we are going to solve the plane stress problem. Okay, so we have defined the field, the displacement field, and we have defined the equations that are going to be solved. Next, we shall go to boundary conditions, right? In the boundary conditions, we will now define the boundary. We'll click on this new, and you see the Dirichlet boundary condition is there. Displacement, force balance, displacement as X component, force balance is also X component, and we want to fix the left boundary, right? So left value should be 0, and this should be the left boundary, and we'll click on OK. So the left boundary is, the displacement is 0. We also want to, the X displacement is 0. For the bottom boundary, we want to also ensure that the Y displacement is 0, right? So it is Dirichlet displacement. We will click on the fill component, and we'll change that to Y. Here also we'll click on the equation component. Yeah, and change that to Y. The value will also be 0, and we shall change the boundary to bottom. Okay, so the bottom boundary, there is no displacement along the Y direction. We'll click on OK. So we have two boundary conditions defined now. Now the right boundary we will define. We'll click on new. So displacement, we'll change that to X. Force balance, we'll also change that to X. And we shall assign a value of 10. So the right boundary pulled will be displaced by 10 pixels, right? And the boundary we are going to give it right boundary, right? So we have these three boundary conditions we have applied. So click on OK. So boundary condition 2, and boundary condition 3, right? So these have all been specified. Okay, so next we shall go to scheduled output. What are the outputs that we need? We will click on new. We'll just click on, so this output is update graphics. We'll click on OK. And schedule, when do we need the output? Schedule type is absolute. We only need it once because it's an elastic problem. There is no time dependency. Okay, and the destination would be graphics window. There are a few other outputs that we need. The output will be for the bulk analysis type. So in the define output name, we are going to name it as average underscore strain underscore xx, right? And so this would be scalar. This would be under field. We will click on strain, and the data type will change that to let's see if it, the data type will change that to engineering strain if it allows me to. We'll change it to elastic strain, so XX, and operation we will click on average, right? We want to find the average for the entire mesh. So average strain XX, we will click on OK. So that is the one output that we want. We want absolute once, that is only once we want the output. Destination, we will have the destination displayed, the results displayed on our message window. We'll click on OK. We click on new once again. We want the average strain epsilon YY, and we shall change the component to YY. Average, everything else remains the same, right? We'll click on OK. And again, the schedule is only once. Display destination is the message window, but you can also save it in a text file if you want to. Okay, and finally, we will calculate the average stress underscore XX, right? So this is scalar, it's not a strain. Stress is momentum flux, so you will have to select flux. So stress component XX is the component that we want. Right? There are other components, but today's we are only interested in the X. Right? So it's a operation average. We'll just click on OK. Schedule again only once. This graphics is on the message window. Okay. So we have scheduled our output. Finally, we will go to our solver. We'll click on the default solver here. We'll click on set solver, everything is, so we just increase the number of iterations from 1000 to 10,000 just for the sake of safety, nothing else. Displacement in initialization, we will set the displacement uh, as constant. The initial x and y displacements are 0. The z displacement is not needed in this problem, but still we need to specify it. So I'm specifying everything as 0. Right. So now is a very good time that we can save whatever we have done as a Python log. Right. So let's see where we can save that. So we will scroll. We shall navigate to the folder where we had saved our results. Okay, and we shall just name it as, we shall give 900k underscore t3, that the image name, underscore 1024 underscore tension x underscore direction, right? So we save that and mode is right. So if we do so, whatever we have done up to this point, that will be saved as a Python file, which we can use later on. Okay, we can use, if we have another image, we can just change the image name in that file and we can use the same options later on. Okay, so once everything is done, then we'll click on solve. Okay, the problem is being solved right now. Okay, so it has already executed. Let's see. Okay, so okay, so average stress, strain, say it has executed. It is calculating the strains, stresses right now. It will take a little bit of time. Hopefully, I'll be able to finish that. Okay, the stress it has also calculated. Okay, so it has calculated all the values, right? And if I would, uh, if you look at this graphics window here, you can see the deformed shape as well, right? You see that it has extended along the x direction. It has also shrunk from the top a little bit, right? So that is also visible. Okay, so now since we have very little time left, let's go to the analysis. So what we will do from here is we shall go to the message window, and from there we shall copy the value of average elastic strain, right? So this is the second value, 0, comma, the second value that we have. We'll copy that, and I have an Excel file open. So the strain xx, I'll copy the value there, right? So that is the value of the strain underscore xx, strain underscore yy. Let's see, is, where did that go? Yeah, so this is here, strain underscore yy is, yeah, minus 0.004 something. I'll copy that. Right, and the stress value I also need. Let's see, I'll copy the stress value from here, from message window as well. So this is the stress value in MPa, right? That's why this looks such a big number, right? So that's the stress value in MPa. Okay, so now we have, so this is, we are given a displacement along the x-axis. Number of pixels along x-axis is 1024 because it's a 1024 cross 1024 image, right? So we need these two values, right? So these two values you will need beforehand, right? So what is the displacement you are applying and what is the pixels along the x-axis? So let's find the Poisson's ratio. Poisson's ratio is nu underscore xy, and that is equal to negative of the strain yy divided by the strain xx. If you do that, so your Poisson's ratio comes out to be 0.413688 something. So that's your Poisson's ratio. Now let's see if your one thing is to check whether the results that are being given out, whether this strain is correct or not. We can check, verify that. Our applied strain, we are given a displacement of 10. If I divide it by the initial length of the microstructure, which is the 1024 pixel, you see these two values, they must match. And if they are different, then you have done something wrong. Okay, your boundary conditions application was something bad. Now coming to finally the final property that we want to predict, the elastic modulus. Elastic modulus is the average stress divided by the stress strain xx, right? So we do that. So that gives us our elastic modulus in Pascal. If you want to give our answer in GPA, we divide it by 10 to the power 9. So elastic modulus is 88.164 GPA, right? So in this way, one can find the material properties, elastic modulus, and the Poisson's ratio for a microstructure that has been generated by mu2mec. Okay, and this is what mu2mec is also doing inside. Okay, so it is not visible to you, it is what mu2mec is doing inside. I just went through all the steps so that you can have a better idea, a better understanding of the issues of how mu2mec and OOF2 are working together. But OOF2 can do a lot more, as I have mentioned. If you are not interested in mechanical properties, if you are interested in let's say other kinds of properties, you just have to go to materials, and there are so many different kinds of thermal, conductivity, heat capacity, or electric, dielectric permittivity, or any kind of couplings like thermal expansion, piezoelectricity, piezoelectricity. All these different kinds of coupled material properties, you can, if your material is in, has a microstructure, has multiple phases, you can, if you can apply the appropriate boundary conditions, you can find their material properties easily. Okay, so I think that's all from my part, right? So with that, I will stop sharing. And if there are any questions, please don't hesitate to ask. Okay. Hello. Okay, so I guess I have finished my demonstration part, and I think in the next section there is a question answer session.
We have this hands-on session by Albert.
Right. I completely forgot. So I will leave Albert to do the hands-on session, and if there are no further questions, I will wait till the end in the question answer session. Okay.
Yes. Okay.
Oh,
Thank you so much, Kaushik.
thank you.